quite a few listeners on today, and today we're going to be talking about, again, optimizing data center design with CoolSim 4.3. My name is Paul Bemis. Many of you know me, and just to give you a little bit of background on myself, I am the founder and owner of Applied Math Modeling, and we're responsible for the CoolSim data center modeling application. CoolSim is a very easy to use, effectively front-end processor that uses software as a service kind of model and processes these models using the Ansys Fluent software. So the approach here that we took is to take the best CFD software in the world and then use that as the engine and create a very easy to use interface for it called CoolSim that allows you to solve complex CFD models using a subscription service that is correlated to use, so that if you're not doing a lot of this, you only do it occasionally, then you don't have to pay as much. So we try to get the cost out of it. We try to get the product to be a little more simple. And I'm real happy today to have Magnus with me. Magnus Herlin is with the company Ansys, A-N-C-I-S, and Magnus, if you'd like to just introduce yourself, that'd be great.
Yes, that was good that you pointed out the difference between Ansys and Ansys.
Yes, I know.
Differently, but it sounds the same.
All right,
anyway,
right.
Ansys Incorporated is a consultancy that works on environmental and energy solutions for data centers. I just want to mention three things here that maybe add a little bit to that. We have done CFD modeling for a number of data centers to improve the design and or the operation of data centers. We have also been the project manager for about 5 years now for the U.S. Department of Energy's Data Center Energy Practitioner Training Program. And as you know, data center is becoming more and more complex. And when something's becoming more complex, we need better trained people, and that's what that program is all about. We have also developed performance metrics for optimizing energy and thermal conditions in data centers. And these metrics have been implemented by many CFD and DCIM vendors. And Paul will now demonstrate how only 3 metrics can be used to make sense of a lot of data coming out from CFD modeling. Obviously, data becomes valuable only when we can effectively use them. So over to you, Paul.
Thanks, Magnus. Now, let me just, for the audience, describe the two of us and how we're working together. I share Magnus's motive to try to reduce a lot of the complexity in terms of volume of data that comes out of CFD modeling to a set of metrics that are easy to understand and easy to use for optimization. When I first was introduced to these metrics that we'll be using today, I found them to be very valuable, very concise, and I started working with Magnus to try to incorporate them into our software, and we have done that very successfully, I believe. So we share a common passion for trying to take complicated stuff and simplify it to the point where it can be used quite easily and quite effectively. And today I'm going to take a look at 2 data centers. Now, these data centers that we use in these webinars are real-life data centers. They come from various locations. Sometimes they're provided to me by our customers on the CoolSim side. Today, certainly one of them is, the first one. And we're going to take a look at them, and we're going to use the same exact methodology to optimize them. Now, for those of you listening in on the webinar, if you have questions and you want to ask us questions, we'll try to save time at the end, usually about 15 minutes, to take questions. And the best way to do it is to use the chat window here in this GoToWebinar session to type in a question, and we'll go ahead and try to answer them online, as many as we possibly can. It's the easiest thing to do, considering microphones and feedback and all the rest to it. So today we're going to take a look at 2 designs. They're both non-raised because that is becoming popular. It doesn't matter really with respect to optimization, but these are non-raised designs. The first one is a floor-mounted upflow unit, kind of a classical upflow unit, which blows cold air up and uses ducted supply. The other one that I see a little more often these days is what they call a rooftop. These are sitting on the roof and blowing down. Also could be the same exact model for a free air design. And we'll talk a little bit about free air or air side economizer here during the session. The objectives of the overall webinar are to build a model of the design. In this case, validation is not possible. We always encourage you to validate your models. If the data center already exists, it's important to build a safety model and then go take a few measurements to make sure your model is predicting what the current situation is. And then, of course, you perturbate it or change it to understand what it's going to look like under certain conditions. In today's examples, they're new designs, and so we don't have them built yet. This is both the beauty of CFD and in some cases the constraint. You don't have anything to measure it against, so you're trusting the mathematics and the computation to give you, or to at least lead you in the right direction. And in that case, it's used as a guide us in the right direction, so that when you enter the design or you look at a variety of designs, you can still iterate to the best one because it's a comparative study. And what we're going to do here today is perform variations to optimize the design. And the methodology we use is always the same. It is first get the airflow balance correct, adjust it, and then it is start to work on air supply temperature to both improve the energy efficiency as well as optimize the design. And then what we do is we use these metrics called RTI and RCI, and we drive them towards 100%. To get to the first two, which are airflow balance and air supply temp optimization. And then we use the model for what if. In particular, the thing you want to be careful of in data center design is what if a unit fails, or you have to take a cooling unit offline to service it. If that happens, what does the room look like? How does the design perform under various conditions? And by the way, there's more than one air handler in the room typically, so you're going to want to study the failure condition of all of them, all the various combinations, which means you need to make a series of runs, a series of simulations to do that. And those are easily done using a tool like CoolSim. So Magnus, these slides, the next couple, actually come from the DSET training, the Data Center Energy Practitioner training, and I ask you as the instructor of that session to just go ahead and review a couple of these slides, and just let me know when you want to move them forward, and I'll do it.
Thanks, Paul. Yes, the four next slides, they're from the DSET program, and we have that at the first session. Get that noise from your microphone, I think.
Oh, okay, sorry.
So to really make this as easy as possible, air management is really designed to avoid mixing hot and cold air in a data center. And what can happen if you don't have that balance that you want to have in a data center? You can get first of all, you can get recirculation, that the hot air coming out from the service on the rear finds its way back to the front and are going in again. And of course, that intake air is hotter than you really want them. If you're providing too much air into the data center, you get something called bypass. And that's not good from an energy efficiency standpoint because you're depressing the return temperature to your chiller. So sometimes I say that what we want to do here, we want once through cooling. What does that mean? It means that each microscopic air cluster just goes through the electronic equipment once. Let's see. Next slide, Paul. So why is this so important to look at air management? Three key things. Thermal management. If you have decided to operate to a certain temperature range going into your servers, air management is the tool where you can actually arrange it to be within that range. The second is energy management. Like I mentioned, if you're supplying too much cool air to your space, you're kind of killing efficiency of your cooling system. And the last one is capital management. If you do arrange your air management, you will notice that you can increase the capacity of your already installed cooling system, and especially your rack floor. Next, please. Everything comes down to this balance between thermal management of your electricity system and how much energy you're using for cooling the environment. And that's a delicate balance, and some operators might have more emphasis on thermal environment and some others more on the energy, but that's like a business decision. So the goals with air management is provide higher supply air temperatures, lower supply air flow rates. If you can't do these things, whatever you do, what you think is air management, is not going to pay off. You need to increase the supply temperature and lower the airflow rate. And that's the only way to make it more efficient. And at the same time, want to maintain efficiency. And the results will be improving chiller efficiency, reducing fan energy, ensuring server conditions, and of course, this is very important, out here in California, they're building data centers with just free cooling, with airside economizers, and if you have good air management, you're increasing the utilization of an airside economizer. Over to you, Paul.
Thank you, Magnus. To achieve these results, we are going to use in our webinar today a couple of metrics that we find are very important. These were first developed by Magnus at his organization with a lot of help from him and working with Department of Energy. And the first one that we review, and we review these each time, so for those of you who have heard them before, I do apologize for that. But the first one that we're going to do is Return Temperature Index, or RTI. And I tend to use the flow ratio here more than the delta T's because, of course, we're modeling CFD flow. So here what we have is the rack flow rate in the numerator divided by the air handler flow rate in the denominator. And this becomes your return temperature index. And it is a measure of the net bypass or net recirculation air of the air handlers in the data center. So if it's balanced, it should be 100%. If, however, it's greater than 100%, then what you're going to have is the rack flow rates are going to be higher than the air handler flow rates, and you're going to have a net rack recirculation. The air handler doesn't have enough air to supply to the racks. Therefore, the rack only has, and these are the servers really in the rack, only have one of two choices. Either they're going to start to stall because there's too much pressure differential across the fan, and therefore the flow rate diminishes, which causes your equipment to heat up and failure modes to occur. Or, as Magnus suggested, it's going to pull air from the backside around to the front side of that server in the rack and cause a recirculation, which would, of course, be detrimental to the life of the server. So the first thing we look at is RTI in all these studies. The next thing we look at is what are the temperatures. In particular, there's a range that you want to operate within. The ASHRAE recommended range is 64 degrees, 64.4, right here to 80. That's generally where you want to run. In fact, many will argue you want to run 77 degrees or lower because the fans inside these servers are becoming multi-speed, and they generally trigger to a higher flow rate at around 77 degrees. So you certainly don't want to be higher than 80, or you begin to defeat the purpose of what it is you're trying to do by reducing the supply air. And RCI high is taking a look at how your racks overall are complying with that specification. And the details of how it's done are less important than the fact that we have a metric here, I think, Magnus, you would agree, that looks at this and calculates it. And what you want to try to do is make sure you don't have any areas on the rack, inlets, that are over temperature, that are over that specification. So as a percentage, how are you doing? You want it to be near 100. 100 would be great. If it's over 100, then you're in bad shape. Good is around 90 to 95%. Acceptable, 90 to 95, and poor is less than 90. Now, you can fail in both high and low. In other words, you can run these racks too cold, and I see an awful lot of that. I see an awful lot of very cold racks, and in CoolSim we actually fail them if they're too cold. And some people will say, well, why are they failing? And the point is you want to be within that range of 64.4 to 80 in order to optimize your energy. You can always run too cold, but it's going to take a lot of energy to do that. Or too hot, you run into reliability issues. So the methodology we use for creating a CFD model is build it using specifications, usually drawings or photographs. Avoid small details because what you want to do is capture the big denominator, the big parameters, the dominant parameters. So little things don't matter that much. For example, underfloor obstruction, if it's not 30% of the cross-sectional area of the underfloor, you can generally ignore it. Focus on the big things first. You can always dial these models in tight later. It's a great thing about a model. You can increase its fidelity over time if you want. But it's the big things you want to get correct first, like placement of inlets, outlets, where are the racks, placement, number of tiles, percent area open for the tiles, height of the room, general big things. And using average watts per rack is an excellent way to begin. You can always dial it in tighter later. You can get the wattage very specific within the rack if you want to, and according to its vertical height if you'd like later. But start off with average watts per rack. And in particular in a new design, you don't really know what's going to be in there anyway. So average watts per rack really works well. Now, and then you use the model to determine the optimal operating point. The governing equation here that we use for all of this is that it's a convective heat flow equation. We only are looking at convective heat flow in these models. And it's the heat transfer is equal to the flow rate, the mass flow rate, times the density of air, in this case, times the specific heat of air, times the change in temperature. Return supply. Same exact equation for the cooling unit as it is for the rack, of course. So what you really want is the delta T's to be exactly the same, because most of this other stuff hopefully is the same. You get the aggregate flow rate the same between supply and demand. Density doesn't change, specific heat doesn't change. So you can see where this turns into a relationship between flow rate and delta T for a given heat load. So the steps we use in the optimizations that I'm going to show you are, number one, adjust the air handlers. You can call them cracks or craws or air handlers. Adjust those to drive that RTI parameter towards 100%. And step two, then begin to turn up your supply air temperature so that you get it within range and preferably as high as you can without exceeding range. And that will be your optimal operating point. At that point, what you simply need to do is make sure that you're okay for failure mode. In other words, what if one of these units drops out? Can the others cover? You want to cover that condition. But for the most part, in a steady state kind of situation, driving RTI to 100 and then going for a supply air temp is the way to optimize the design. Rule of thumb, generally people say, for every degree F, you get a % increase in your mechanical efficiency. It's actually, as you can see, a little better than that, depending on the situation. And as Magnus pointed out, if you've got any kind of economizer here, whether it's air side, water side, if you can increase supply air temperature, the window of opportunity for using outside air to cool your data center, either directly or indirectly, goes up tremendously. And that reduces your energy by a tremendous amount, a significant amount. So raising supply air temp is important for a couple different reasons. So I've got a couple of models here. Again, we built the model. We're using the system to predict the effect of change, look at RTI, go for supply air temp, and then we use air management techniques to improve airflow in certain cases when we need to. So I'm doing this a little bit differently this time. I'm going to drag into, I have two monitors up, and I'm going to drag this CoolSim model in. And this is a model that was provided to us by a company, CRB, out of Cambridge, Massachusetts, the user of CoolSim, Dana Etherington, who may be with us today in the audience. And he built this model, very, very nice model, very intricate model. You see here, this one, Magnus, is ducted supply. These are upflows. So the hot air is coming back, being pulled through these ducts into a classical upflow cooling unit, and they're being piped up into a big header and then being supplied to these series of subducts and then down into the cold aisle. So this is, sometimes they call these designs a bathtub design. It's because you're pouring into a bathtub or, the cold aisle. You're using the advantage of density of cold air because it wants to drop and sit in that tub and fill it up with cold air. In this particular configuration, I do not have a return ceiling plumb in place. We'll study that in a moment. But I've often seen these kind of designs because it's a big room. That's a 12-foot ceiling from this point up. It's right around 12 feet. And so these racks, as you can see, have chimneys on top. These are passive chimneys that are dumping heat out of the rack and straight up into the room. So you would think the hot air flows up here and then back through these returns. You've got your supplies here. Everything should be great. So we've built the model, and these racks are sitting in a corridor off to the side. And one of the things we've done in CoolSim, which I'm showing to you here, is we've added in the latest release this Presimulation Report. This Presimulation Report allows you to review the input that you've put into the model. For example, you can see this one is a 6,000 square foot design with 30 racks and 30 rack rows, 82 racks, etc. One of the things here that's kind of interesting is you can look at your RTI number up front. RTI does not depend upon I don't need to run a simulation to know what the RTI is. All I have to do is compare the total amount of air supplied to the total amount required by the rack. And the rack has a requirement that's correlated to its heat load. Effectively, for every kilowatt of heat generated by a piece of electronic equipment, you need approximately 156 CFM of airflow in order to keep it from running away thermally, in order to keep it stable. So by simply assuming a 20-degree rise in temperature, by the way, which is normal. You can make it higher if you want, but 20 is a reasonable number, a conservative number. So a simple way to determine your demand is to take the total load that you're planning to put into the room in kilowatts and multiply it by 156, of course, English units. I'm sorry for my European friends. I actually don't know the SI value for the same thing, but 156 CFM per kW, and see what the number is, and then look at what you're supplying and see how close they are. So here, Magnus, you can see we're at 73.88, which suggests we're going to have some net bypass airflow of those cooling units, right?
Correct. Correct.
So we know right away, before running any simulation, that the design is not optimized by looking at this. But depending on where the air goes, I mean, just because they're matched, Magnus, doesn't mean our racks are safe, right? Depends where the air goes.
No, that's correct. I mean, even if you have a situation that the return temperature index is 100%, that we have a perfect balance between what we're supplying into the space and what goes into the electronic equipment, it does not mean that we don't have bypass in one area of the space and recirculation in another. But as Paul is going to show here is that that is going to be, the red flag is coming up when we're looking at the RCI, the other metric.
Right.
If you do have recirculation in one space, you will see that RCI high is going to be poor.
And we don't know RCI until we run. So we're going to have to make a run to see RCI because that's we're mapping the airflow. Now, before we go, let me just point out here, here's my cracks. I have 6 of them. They're operating at 57 degrees of supply air temp. They're quite cold. And they're delivering 13.7 of flow. Now, this could be a VFD design, and it doesn't matter. It can be a constant design. All you need to do is adjust these to look at different design points. In other words, if you want to look at the extreme point or the minimum point, all you need to do is adjust these values to see wherever you would like to look at the state of the system using safety modeling. Okay, so now the output in CoolSim, when it's done, shows up here in the reports. So what I have here is a set of reports. Now, the way it works in CoolSim is you're able, and I'll go back to the input for a minute, you're able to run multiple variations concurrently. And this is a nice feature. This is a new feature that we added at 4.2. And it'll allow me to run up to 4 simulations concurrently. And I have the ability to turn on or off the cooling units. For example, if I wanted to look at failure analysis. I have the opportunity to modify airflow. And I have the opportunity to modify supply air temp. So everything I want to do here to optimize this design can be adjusted using a single panel from one location. And then when you submit it, you submit all these variations at once. I've got 4 jobs set up to run. And I can run them all concurrently because I'm running on a cluster. The way the CoolSim works is it launches the jobs on a remote server on the cloud, and I can run multiple jobs concurrently. And when they come back, I can look at all the results in one place. Very nice in terms of summary. So here they are, Magnus. Here's what I ran. The first run I made, run 0, I ran the flow rates at 12,000 and the supply air temp at 57 degrees for all of them, pretty much the way it came to us. I then, in run 1, you see what I'm doing here. I'm going for optimization. I'm beginning to reduce the airflow down to get it close to what I need it to be to drive RTI to 100%. So I take one step, and then run 2, I take another step. I move supply air temp up a little bit to 65 degrees. And then in run 3, I went directly for the exact RTI, 10,200, and I went to 75 degrees. So this is my optimal case over here, and I'm stepping to it. This is a classical optimization set of runs where I start off with the initial condition, modify one parameter, then begin to modify the other parameter to get to where I need to be. So let's take a look at our results. Let's look at results for run 0. Now, run 0, now the easiest thing to do, and here's the model. And now as I manipulate this model, sometimes a GoToMeeting or GoToWebinar gets a little touchy, and the audio tends to bust up a little bit, and sometimes the video busts up a little bit, so bear with me. But let's first take a look at the summary report. The summary report is a text-based report that gives you a tremendous amount of information. For example, it shows you on your cracks exactly what you've got them set at. So you see here, delivering 57, I'm returning 74, 12,000 each. Here's the amount of heat eliminated or rejected by each one of those units. The energy report lists our RTI and RCI. And as you can see, we're at 84% on RTI, which means we've got too much air. But our RCI is 100%. It's happy, right? Because you can have too much air and have temperatures really low and RCI high, be 100%. Right, Magnus? Because we're not experiencing any hotspots.
Yeah, Paul, maybe we should emphasize here that the goal here is to drive both the RTI and the RCI numbers to 100%.
Right.
100% is the maximum they can have.
Right. And RCI low here, 59%. What's that tell you, Magnus?
Well, that, of course, if RCI low is below 100%, that is the ideal. It means that the space is overcooled. You have too much cool air coming in.
That's right. So now we understand that. We look there first, and now we can look at graphics. This is the beauty of CFD is you get to look at. And the one I always go for first is rack inlet temperatures. Now the way we look at rack inlet temperatures in CoolSim is a few different ways. One is, of course, we have the full range. Full range is when you take the amount of temperature as seen by the CFD calculation and you spread color out across it. So the minimum inlet temperature, these are rack inlets. I'm looking at color contours on the front of the racks because that's the most important. That's what we're interested in, the inlet temp. And we have 60 degrees is the coldest it sees, and 69 degrees is the hottest that it sees, and we simply take color and we spread it out across it. But it's not a conformance plot. All it is showing you here is the total range of temperature across those inlets, colored by, or shown by color, according to color. The other one that I always look at is conformance. This is a conformance plot right here. This is if you're within the ASHRAE recommended temperature range for rack inlets, it'll be green. If you're above it, it's red. If you're below it, it's blue. So right here we can see that we're too cold. In most of that room, Magnus, we're too cold, right?
Right.
And there's two reasons for that. One, we got too much air, and two, we're running at too cold a temperature. But the contours themselves tell you something else about the room. That tells me that over here in this corner I've got trouble. That's going to be my problem spot over there because that's warmest compared to others, and a little bit over here. Now to look at the airflow itself, we have other plots such as return air here. This is the air coming back from the cooling units, from the racks to the cooling units. Now in this case, the air comes back through these channels here on the side, so it's coming back into this ducted area here for the most part. But let me bring this around, and I'm going to do something here. I'm going to use a couple of keystrokes to get this thing lined up so we can see it. And turn off perspective. And we also now have the ability in CoolSim to remove some of the obstructing blocks. And I'll take that one out. And so now we can zoom in here and take a look at this and see what's going on, and we see quite a bit of recirculation occurring over in this area. I mean, there's a lot of mixing going in there, Magnus. It's not very clean, is it, with respect to, because these are returns, remember.
Yeah, the space is not really symmetrical, so it gets kind of messy when air needs to go from one part to another part of that room.
Right. And that's why if we look at it from the top view, which is this, you see over in this section here, we're having a little bit of recirculation, a little bit of trouble. As the air comes over and starts to go towards these cooling units, it collects over here. We have more return going on over here, which is going to create higher temperatures. For example, if we look at a slice of temperature here, if we take a look at this one and bring it around so we can see it, you can see the same effect. Quite a bit of temperature occurring over in this section of the room as compared to the other sections. It's piling up. You got two hot spots sitting right there, as a matter of fact, and this whole section is problematic. And there's animations built. There's a bunch of sequencing here that's done. We won't go into all of it in terms of what's provided. This is supply paths, etc. But suffice to say that we've got some issues there in that particular design. So that's run one. Now, just to remind you what we did here, that was run 0. Run 1, we started moving the flow rates down, okay, keeping temperature the same. And then in run 2, we go all the way to 10,200. Let's take a look at that one, Magnus. Because there, if we take a look at our summary report, and again we go for data center energy, look what we got, 99%. So we went from 84 to 99 by reducing supply error, and in this design, we got 100 and 100, both of them. Beautiful.
You can see that, Paul, that when you manage to get the RTI better to closer to 100, went with it.
Right.
And that's quite common actually, because obviously when the RTI is much less than 100, it means that you have bypassed all those.
So now let's take a look again. You can see that our rack inlets are perfect in terms of temperature. They conform. If we take a look at the full range of them, we're still going to see a little bit of deviation. We still got a little bit of heat over there in that range, a little bit of non-uniformity. But look here at the temperature range. It's only 70 to 79. We're seeing just about 10 degrees, a little less than 10 degrees of differential across it. There is still some mixing going on in this room as well. That's, but there's less of it now. You see, there's most of those path lines are now up in the up on top. And again, we can remove some of this so that we can see it a little bit better. But they're not coming down. You see how it's staying up for the most part. See some path lines. You see a little bit of it leaking down here. Right there is a good example of it coming down and starting to get into the inlets. But we have to remember here that we're driving this thing pretty cold. If we go back and we look at our cracks, we're driving this thing at 65 degrees. That's still fairly cold. But if our rack inlet range is up to 80 degrees and we're driving it at 65, that's still pretty darn cold.
Right.
So in run 3, we go a little higher. Again, just to summarize, in run 3, we're driving it to 75 degrees. So run 2 looked good. We had RTI at 100, we had RCI at 100, both high and low. Everything looked good at 65. Let's see if we can go to 75. And here, let's take a look again. And the summary report will tell us an awful lot. And it tells us right here in energy, RTI still 99, but look what happened. Magnus, 42. As we tried to drive temperature up, we ran into problems with RCI high. We're seeing hot spots.
Yeah, and again there, Paul, when the RCI high goes below 100%, that means that we have too hot conditions in the
That's right. That's exactly right. And it can be seen in this one plot. There they are. We got a lot of them, Magnus. They're all out of spec, Not just one, but just look at that. The visual representation is more compelling, really, than the number itself. It shows you just exactly what's going on. And the reason, of course, is because of mixing. So again, if we look at the returns, I look at returns, Magnus, more than I look at supply lately, because it's returns that actually give me the problem oftentimes. It's the return that's not managed as much as anything else. And like I said, it's this stuff in here. If we bring this around and take off the perspective, you can see right there's your problem. I'm only showing return path lines here. There should be no return path lines that far down. The fact that they're that far down in the room suggests that I've got problems. Why are they there? Why are they coming down? Right? So what we did then is we went ahead and we changed the design a little bit here to add a ceiling plenum. So what I'm going to do is just bring that simulation over. I've got multiple copies of CoolSim running here, which you're able to do because we don't restrict the number of copies you can have running. And you see here in this design, all we did was put a ceiling plenum in place. Now, to be honest, the original design had a ceiling plenum. So, to be fair to CRB and Dana and all, this is the way it really should have been represented. What I was trying to show, though, is that the benefit of the ceiling plenum can be significant. And many people will ask me, well, what's the benefit of a ceiling plenum? And here we're able to show it, because now the air is piped directly into this upper environment. It is kept out of that floor range, and the opportunity to optimize it should be higher. So here again, just to summarize, same exact setup. We did the same set of parameters, and over here now run 3 Magnus 10,200, which should drive RTI to 100%, and supply temperature 75 degrees. The question becomes, can we get there now that we've added a supply plenum? And so let's take a look. We go to our summary report. We can tell with just those 3 parameters. And what's kind of fun about this is we went to 100 on all 3 of them. Okay? So by controlling the return air and putting a ceiling plenum in place, we went from 46% on RCI high to 100%. And if we take a look now at our recommended temperatures, they're fine. They're all within range. And if we take a look at that same plot of airflow here, and let me just bring this around, and again, I'm going to use a couple of keystrokes here that are available, and I'm going to turn off a couple surfaces so that we can see a little better. And what we find is no more path lines down low. That what has happened here is the management, the ceiling plenum has managed the return air so it can't get down low and mix with incoming air and drive the temperatures up. It's a mixing issue, right, Magnus?
No, exactly. That's what we said before, that the goal with air management is to avoid mixing. And by installing this drop ceiling, you actually did that's an enclosure technology. You separated the cool air completely from the return hot air.
Mm-hmm. And that solved the problem. So what the metrics do for us is they give us an opportunity to very quickly take a look at where we are kind of in a global sense, in a macro scale, with RTI in particular. And then we can begin to dial in the RCI high and low together with a little bit of air management to illustrate exactly how to get to the optimal operating point. Okay.
So Paul, I'm going to put you on the spot here now.
Mm-hmm.
You know, this methodology you have, that first you're fixing the airflow rate, and then you're looking at the RCI to crank up the supply temperature as much as possible. I mean, I would love to see that this process could be automated in one another fashion. So you first put in your data you have now, and then the system steps through this process, the same process as you do manually now, and it stops when all of those are close to 100, all the metrics are close to 100%.
Yes, you're absolutely right, Magnus, and I agree with you. And I think it's a fairly straightforward thing to do. What you're asking for is to simply hook an optimizer to CoolSim now and let it drive RTI and RCI to their optimal values, and then give you a report that illustrates and summarizes what the optimal point, the optimal operating point for a given data center is. And I think it's a natural next step, and I'd love to do it. So yeah, you and I can work on that. Next release, right?
Sure.
So now let me show you one other design here, because we have a little bit of time, and I wanted to do 2 today. So the first one I'm going to do is, this is an overhead design. This is actually the second one I'm doing today. This is an overhead design, and I brought this one up, Magnus, for a couple of reasons. Number one, I'm seeing a lot of overhead designs. This is, again, non-raised floor data center. So you see I'm sitting on the floor. And what we have here is a model of rooftop, what they call rooftop units oftentimes. And they sit up on top, and they dump air down into, again, sort of a bathtub. It's kind of a bathtub effect, right? You can put end caps on these things, and it would be like a bathtub filling up with cold air. This also could be used to model air side economizer. So the idea would be the air comes out, goes up through these grills and into the atmosphere. This would be the atmosphere. and from another source you get cold air coming in. That source would be outside air. But from a CFD model point of view, it doesn't matter because, again, all we're looking at is, all we're really interested is the amount of air coming into the room, where is it coming into the room, where is it exiting the room, how much, flow rate, and its temperature. That's it. That's all we're really interested in. So this could be air side economizer, or this could be mechanical, or a mixture of both. Doesn't matter. From an optimization point of view, all we're doing is looking at the various cases of the various scenarios to A, find the optimal run, and B, make sure that under a failure mode we're safe.
Hey Paul, maybe it's worthwhile to point out, if you could go back to that last, yes. If you look at how symmetrical this space is, that the cool supply air is coming down into the cold aisles, and the return air goes up right on top of the hot aisles. Mm-hmm. It's very symmetrical space. And also note that the space itself doesn't have any dividing walls or drop ceilings. It's really an open space.
Yes, and it doesn't also have any angles, angled walls. We could do that, of course, in CoolSim, but the point is that you're making is symmetry tends to help you, I think is your point, right?
Yeah, that you actually, you want to withdraw the hot air as close as possible to the hot aisles, and you want to supply the cool air as close as possible to the cold aisles. Right.
Yes. Yep. It is, symmetry can be your friend. So let's first take a look at, well, again, let's look at the summary, the pre-simulation report. And this one's kind of interesting. Now, in the pre-simulation report, again, we haven't done a run yet. This is all available prior to submission of the job for processing. We can take a look at the airflow balance, the RTI. This one's showing 103%. So this one says that we've got too much demand from our racks compared to the amount given to us by the cooling units. Those cooling units, if we take a look here, they're set up for 10,000 CFM each, and there's 6 of them. And they're delivering 60-degree air right now at this point. So what we have is 60,000 CFM of supply air sitting up here, but our racks, which are shown here, are sitting there at 10 kW each at 20-degree increments of expected temperature rise. And so we're running into a situation where right from the get-go, Magnus, we don't have enough airflow to make this thing happy, right?
Yeah.
Now, we're not off by much, but we are off. So let's see how it performs. And here, again, I ran a series of runs, not just one, but I ran 4. And over here, I left it just the way it was. And then what I started to do is started to bring up the airflow from the cooling units to try to optimize it, to try to optimize that RTI. So I brought it up 1,800 CFM roughly, 300 each, to try to improve that. And then I started marching up the temperatures, right? Same as before, same methodology. Get RTI set, then start marching up the hill of temperature of supply air temp. And then I wanted to see what happens in a failure case. I ran one with one out to see, and here what I did, assuming we had some kind of VFD, is to run the supply up. These are the supply flow rates here to make up for the fact that one of them is off. So I incremented them by enough, just about, 6. I did 2 each. To be able to supply enough capacity to handle that case in the failure mode, assuming we had a control system on there that would do that. So let's take a look. We'll do run 0 first, and we can take a look first at the summary report, data energy, and what we have, RTI we knew already was 103, RCI 100, RCI low 65. So what that's telling us is we're too cold, right? So we know already that we're not too hot, but we've got an energy problem. We're using too much energy to satisfy the needs of this data center. And if we look at our recommended inlet temps, there you have it. we're too cold, except for the edges. And the reason that we're not cold on the edges is we don't have any containment on the ends of these caps, and we've got some wrapping around going on. If we look at a slice at 6 feet and we spin it around here so that we can look at it from the top and take perspective off, you can see the temperature coming out of that hot range and affecting the inlet temps. You can see a little bit of effect right there. Temperature is right there a little high. You see another hot spot here. So we do have a little bit of bleeding, effectively, that occurs. Let's see if we have any wraparound going on. If we take a look at path lines from the returns, you can see a little bit of wrapping going on, it looks like right there. You see? Where it's coming out of the outlets, out of the backside, and wrapping around and causing that temperature to rise right in those same areas. So these plots match each other, of course. We're just looking at them differently. This is a path line plot. And again, I can use keystrokes here to spin this thing around and take off perspective, and you might be able to see that same effect where you've got the air mixing in over here to cause that. We could look at it from the front as well, or the side, and there we go. Let's look at it here. Perspective off, we can see a similar thing. We've got airflow coming in and wrapping around here. We've got a little going over the top there. That's occurring, Magnus, you can see, and that's of course because the RTI is not 100%. We don't have enough supply air, so those racks have to breathe their own exhaust because they don't have a choice. You know, the only other choice is that the fan in the server goes into a fan curve mode where it can't push enough air, which wouldn't happen in this case because there's no impedance, there's no resistance, and it's just going to breathe its own exhaust. So let's go back now and begin our optimization run. So again, just to summarize, we're going to go run 1 is going to increase the flow, and then once that looks good, we're going to go run 2, we're going to increase temp, and then run 3 we're going to. So let's do run 1 first. We should see here that our RTI is going to be 100%. It is. And look at the other two. RCI high, still 100. RCI low improved a little bit, but we're still too cold. So I don't have any problems with hotspots here. I'm still fine. If we take a look at the inlet temperatures, the conformance plot, you see there's less green than there was, there's less variation than there was before. We're still too cold. So in the next step, step number 2, we start running temperatures up. Here, let's take a look at summary report, data center energy. Look at that, Magnus. Now we're getting there, right?
Yeah, that made it.
Yeah. So if we take a look at our crack performance report here, we see that we're delivering 70 degree air. We set that as a variable, so that's a supply air temp. Returning 90, that's nice, delta T, 20 degrees, 21 degrees. So that's going to make the crack unit happy in terms of its efficiency. We're delivering 10.3. Our RTI is 100%. And if we go have a look at our temperature ranges, everybody's happy. Yep. Symmetry helped us. Now, however, we now also need to look at failure mode. So in failure mode, just to review, if we look at our summary, failure mode here, we increased the flow rate of the other units but kept the temperature at 70 degrees. And the one I shut off here is crack number 1. So let's take a look at that one. The way to tell which crack is turned off in CoolSim is we don't light up the inlets and outlets, you see, so that one's off. So I shut that one off, and let's first take a look at our summary report and data center energy. Everything looks good. And how did our racks make out? And it looks like they did fine. So this is an N+1 design as long as the middle units are off. Now the other thing I did here, Magnus, on one other run is I did a full failure analysis here. So this one I ran. This is another one I ran since I spoke to you last, and we ran 4, and I round-robined the cracks. I turned them off. But I didn't do them all. I did the ones I was most worried about. I did the ones on the ends. right? Because the middle one seemed fine, but as I go to the end here and turn this guy off, I run into a little bit of trouble. So you can see my RCI high is 80 now, okay? And if we take a look, I'm beginning to have a little bit of trouble with here on the edge. Which?
8 is not good. That's, of course, a poor value for the RCI high.
That's
so that
right.
shows here as red.
Right. So this design does have some problems when you lose the end units. There's here, the same thing occurs if I lose any of them. If I lose any of these end units, let's take a look at run 2. Run 2, I turned this guy off over here. Same situation, I've got some problems. Now, I could probably solve that, Magnus, by putting some end caps in place, right? Putting some cold aisle containment in place, because the bleeding that's occurring is around that edge, and you can see it here. Although I've got enough air coming out of the other units, I've got this hot air coming out, and it's contaminating the intake right there and causing some trouble. So if I put end caps in place, that would probably solve it. But I didn't have a chance to do that before we went to the broadcast. So there we took a look at 2 different designs. Just to summarize, what we did again: built the model, set the RTI, increased supply air temp, and in the first one we used air management by putting a ceiling plumbing in place. The second one was telling us we needed to do air management in order to solve the failure analysis, to solve the crack failure. The middle units were okay, but as soon as you lost one of the end units, you started to run into trouble. So at this point, I'd like to open it up for some questions. We've got a few minutes left before the top of the hour. This is optimizing data centers is what we've been talking about here. Using this method, we find it to be fairly straightforward, easy, and cost-effective, and works for both new and existing data centers. So I encourage you to put some questions in here. If you don't have some, I'm going to start taking some that somebody put in place. In CoolSim, the flow it says under the flow is modeled as well. Under the floor, I think. If no, how do we know the flow is distributed in the room? Yes, it's modeled everywhere. The airflow is modeled. If there was a floor, it's modeled there. If it's in the ceiling, it's modeled there. So it's modeled everywhere. One other question here came in about the audience, and it says here, Magnus, can't imagine an average user staying on this topic. I suppose, I think in this person's concerned that we might be speaking over some people's heads. I'm hoping we're not. I'm trying not to do that. It's really straightforward, I think, in the sense that we're talking about the balance of air in the first place and the temperature of the supplies. So I apologize if we're finding it hard to follow. I also, Magnus, get the counterpoint that it's not sophisticated enough sometimes. So you try to walk the middle of the ground, I suppose, with respect to complexity.
I think it's just for the average user it might be a bit confusing, but I think the message here is that you have developed a protocol for looking at different metrics to optimize your air management, and people don't really need to understand exactly these metrics, how they work and what you're doing, but if you can show at the end of the day that you have moved these metrics to the ideal point of 100%, so the space has been optimized, that's an important message.
Yep. The question here, is this an actual data center? I noticed the crack unit has the exact same flow rate. Yes, the first one was an actual data center. The second one, I don't believe it was. To be honest, I can't remember. I think the second one was contrived. And that every crack unit had the exact same flow rate. Well, that's just a setting. We set them to be whatever you want them to be. If you don't want them to be the same, set them to be something different than what they are. The parameters are all variable, so you can set them any way you want. The corollary is, do you feel a simple kilowatt per cabinet is sufficient to give accurate results? I noticed the rack inlet temps are different than the server inlet temps. Is that because there's zero internal cabinet recirculation? The answer is yes. In a first pass analysis, again, you can always add more detail to these things, but be careful of the detail because you can get lost in it. But yeah, when you're doing a basic design, what I find most people do is average watts per rack for two reasons. Number one, you haven't built it yet, so you don't know what they're going to be at all. And number two, you have to make some assumption about rack recirculation and the fact that the people putting the racks in and putting the servers in the racks are going to do their job correctly and seal the rails and so forth. Right, Magnus? I mean, it's hard for us to anticipate.
I think what I do many times when I do CFD simulations for other companies is we're looking at the extreme cases.
That's
if
right.
Extreme cases pass, it means that all other cases in between the extreme cases will pass too.
Yes.
So you can bracket your problem.
Right. You bracket your problem. The other thing that I just wanted to point out there, Magnus, is that you can always get into more detail, more complexity. You can put in CoolSim the wattage specifically in the vertical position. You can build the entire rack and look at leakage inside it, but we have to make some assumptions about what's going to be deployed here. And this at least gives you a set of parameters, at least a range of where the parameters ought to be. In other words, we've done this model, and one could argue that it's an oversimplification. But you and I go into that data center, we know roughly where that crack should be set in terms of flow rate, right? We know roughly what that RTI should look like. So we have a place from which to start. It may not be exact because the real world is not exactly, of course, what we've done in the models. See, the models assume some ideal conditions. But at least we have a good place from which to start. A lot more than we knew without it, which is it had no data, right?
Mm-hmm. No, I think you demonstrated today that when you're moving these metric values towards 100%, just looking at the results, we see that things really have changed to the better.
Yeah. Next question here, does a cross-sectional area of the duct affect the model? Yes. We're modeling the flow inside the ducts, and so you saw in the first model that Dana had stepped the duct down in size, and we do full CFD calculation inside the duct, and so those sizes do change the velocities and the pressures inside the duct. So yes, if you have a duct header and you disable different AHUs, air handlers, the model will show how those ducts flow data. So yeah, it's fully accurate with respect to modeling in the interior of ducts. And it does it quite nicely. Question here about modeling OptiCool systems unrelated to our webinar, rear door heat exchangers. Yes, we can model rear door heat exchangers, and that's not a problem. You treat them very much like you would an in-row cooling unit, but it's sitting behind instead of beside, and yeah, you can model those. And the question here I get a lot, Magnus, this is one, how are the airflows being measured? Is this estimated with sensors? The answer is no. We don't use sensors in CFD. Sensors...
Paul, you're dropping out a little bit.
Yeah, it's probably some bandwidth. But so let me just repeat the question. The question is, how are the airflow being measured? We're not measuring it. We're modeling it. If you know the inlet of the air coming into the room and its flow rate, and you know the rack and its consumption of air, you can calculate everything in the room through CFD. That's what CFD does. Now, where sensors come in and where sensors are important is validating the model. So you run a CFD and you compare it against the values that are measured by the sensors to see if the CFD calculation is predicting what you're measuring. Did that come through clear? Is that okay, Magnus? But in terms of measurement, we don't use measurement. We use it to calibrate the model and correlate the model, but not as part of the model. Another question here, how does CFD capability adjust or accommodate for moving loads? I'm a fan of CFD, but the dynamic loads have a challenging for static solutions. Well, again, as Magnus pointed out, what you do with CFD is you look at your extreme cases. We used to call them in engineering the corner cases, right? What we want to do is understand the worst case conditions, the best case conditions. What are the corners? If we know the corners, then everything inside it, everything to the interior of that design space ought to work. So dynamic loads, what is the worst case condition? Let's look at that. What's the best case condition? Let's look at that. Everything in between should be fine. And you are right, Greg, the data center is becoming a dynamic situation. It's becoming a transient situation. But you can still use CFD to get close to where you want to be, closer than you could without it. And you can study the corner cases, the extreme cases, very effectively to make sure your solution will work in those corner cases. So, okay, that was the last question we had. We're out of time. Magnus, I'd like to thank you for being with me today and helping me make some of these points. I do apologize if we talked over anybody's head. That's not our intent. We were trying to be down the middle here and tried to simplify it a bit. I guess one way to look at it, Magnus, is if they think it's complicated now, before it was much more complicated, right? I think the RCI and RTI work you've done to simplify this down to a few metrics has been enlightening and very, very helpful. So I think it's much simpler than it once was. So thank you for being with us today. I will make a recording of this broadcast for those who weren't able to be here, and I can also produce a professional certificate for credit if you would like. Send me an email at the end. Our email addresses are at the end of this presentation here. So if you would like to contact either one of us, our email addresses are here. Please let us know. Provide us feedback if there's things you think we can do to improve it, short of technology such as GoToWebinar, and that sometimes that causes us some issues. Please let us know, and we will try to improve it in the future. Thanks to our audience. Thank you, Magnus, and everybody have a good day.
Thanks, Paul.
Thank you.